Hello. So today we will be talking about the Haber process. In order to understand the Haber-Bosch process, we must go over the following items. This includes its history, the catalyst that is used, the ideal pressure and temperature that may be used, how we're able to recycle certain parts of the Haber process so that we are being efficient, its applications, and the environmental effects that the Haber process may have. So let's start with the history of the Haber-Bosch process. Before we could make ammonia artificially, it was found in farms, forests, and fields. This includes animal waste, plant residue, and organic matter in soil. It was initially used for dyeing clothes and preparing leather, as shown in the image below on the right side. In 1909, Fritz Haber and Carl Bosch developed the Haber-Bosch process that was due to the increasing global demand of food. It became evident that ammonia could be used for fertilizers such that they would increase the yield of crops throughout the world. What is happening in this process is that nitrogen and hydrogen gas are being placed in heat exchangers that are capable of making them come together to form ammonia. This must be done through certain conditions as shown in the diagram, which includes having a catalyst that we will go into further detail later on, and not all of the nitrogen and hydrogen will come together to form ammonia. So some of the nitrogen and hydrogen will be recycled later on, as shown in the middle of the diagram, where the nitrogen and hydrogen are returning back to the initial vessel. But the ammonia that was formed will become liquid form that towards the end of the process will be able to take it out and form other useful products out of this. Now we will go into further details about the catalyst used. So what is a catalyst and why will we use them? Catalysts increase the rate of reaction in reducing the overall activation energy, but they will not alter the position of the equilibrium. What this simply means is that catalysts will make the process a lot faster, but they will not increase the yield of ammonia or decrease its yield of the product. Does the catalyst just simply acts as an improvement in the rate of reaction. A heterogeneous magnetite-based catalyst is used that is mostly made out of iron 3 oxide. It is mixed with some metal hydroxide promoters, which include aluminum 3 oxide, calcium oxide, and potassium oxide. These promoters are able to improve the performance of the catalyst such that they're able to make sure that the bonds between between both gases is able to better be broken, especially with nitrogen gas that has a triple bond that is extremely difficult to break without the help of the catalyst. We will go into how pressure plays into the Haber process. Due to experimentation, they have come up with an ideal pressure of around 200 atm that most industries will use because of the fact that any larger than this amount will mean that the systems that'll be in place will be too expensive to maintain and have, to the point that the ammonia gas that is produced will not be creating enough profit for them to be able to still maintain and have these very high pressurized machines, even though because of the Le Chatelier principle, we know that in increasing the pressure, we will be able to increase the yield of ammonia, but it will not be profitable to most businesses. Temperature is another factor that we must consider when talking about the Haber process. The Haber process is an exothermic reaction, which means that it releases heat, and thus it requires low temperatures. The lower temperatures counteract the release of heat and produce more heat. Initially, the reaction was slow, and so high temperatures were used to speed up the reaction, but this would result in a lower yield of ammonia. This was then resolved by adding a metal catalyst, the magnetite-based catalyst that I discussed earlier, and this catalyst would allow for lower temperatures that would yield more ammonia, all the while speeding up the process. However, due to adding the catalyst, low temperatures were possible to yield more ammonia, but it still required a high temperature in order for the catalyst to react with the nitrogen and hydrogen molecules that would be able to break down the nitrogen and hydrogen molecules into nitrogen and hydrogen atoms. After many trials of manipulating these three factors discussed, being pressure, temperature, and the catalyst, in the production of ammonia, Haber and Bosch decided that an ideal temperature range would be around 400 to 500 degrees Celsius, which would allow for the nitrogen and hydrogen to react properly with the metal catalyst, as well as being low enough to shift the equilibrium towards the ammonia. Now we will go into how recycling is an important component to making sure that this process is not as wasteful and being able to use the reactants again. In one round, only about 15% of the nitrogen and hydrogen are converted to ammonia. What this means is that the Haber process is not able to use all of the hydrogen and nitrogen gas to make ammonia, and thus a lot of the reactants is being lost in this process. Thus, for the reaction to be effective and not wasteful, Haber found a way to continually recycle the excess hydrogen and nitrogen that is left over. He developed a system that recycled his gas over the catalyst after separating the ammonia formed by condensation. So once the gases were passed through the system, they were able to put it back into the initial heat exchanger, where it would pass over the same 4 beds of catalyst at a very high temperature and potentially turn into more ammonia that they could later liquefy using the same process, and this process would just happen over and over again to make sure that none of the reactants that as much reactants are being used throughout the process. When all the nitrogen has reacted with excess hydrogen, there is a 98% overall conversion, thus indicating an increase in efficiency. So using this process of recycling is very important for the Haber process to not be so wasteful and be able to make their money count and not have to invest in more supplies than needed. We will go into the applications of this liquefied ammonia that is now produced and how it's used throughout the world for different things. About 4/5 of the ammonia produced goes into the fertilizer production. This includes common manufactured fertilizers such as ammonium sulfate that is produced using some sulfuric acid, ammonium phosphate that is produced using some phosphoric acid, and ammonium nitrates that is produced using some nitric acid. Ammonium may be also used in the textile industry in making acrylic fibers and nylon 6 fibers that are able to be used for different types of clothing or any types of material that may use this type of textile. Industrial enclosed refrigeration systems make use of anhydrous ammonia as a refrigerant because of its properties in high latent heat, low vapor density, chemical stability, and low iron corrosivity. Because of these properties, we're able to create refrigeration systems that better insulate whatever whatever it may be trying to insulate inside of the system. Ammonia can also be found in many of our household cleaners that include window cleaners and ammonium salts. These ammonium salts are found to be used in detergents for liquid dishwashing solutions. Water purification systems may use ammonia in addition to chlorine to better purify municipal and industrial water supplies. It is also used in waste management that they add small amounts of ammonia that are used as a source of nitrogen for the bacteria that may be used in these waste treatment systems, such that the bacteria is able to grow and perform better in these conditions to break down whatever substances they have to break down in the waste management systems. Finally, what are some of the environmental effects that the Haber process may have? Ammonia is one of the main sources of nitrogen pollution that as a result can negatively affect biodiversity. The emissions have been proven to be destructive to the ozone layer and thus contribute to global warming. Crops are not always able to consume all of the fertilizer, and the residue that sits can get into all of our environment, including the groundwater systems, that can negatively affect the animals and species that exist in these habitats. In conclusion, the Haber process is very essential to the history of humanity because of the fact that it has been able to mass produce a lot of useful products that include fertilizers and household cleaners. It is essential mainly because of the fact that it is able to create fertilizers that improve the yield of crops, and in improving the yield of crops, we're able to feed the exponentially growing populations throughout the world. And the process still has a lot of room for improvement. We still need to improve how much carbon emissions is being made because of the Haber process, and this is due to the fact that the Haber process is very dependent, like many other industries, on fossil fuels that is only going to keep making the issue more problematic with time. And we need the Haber process is still largely inefficient as far as how much nitrogen and hydrogen gas is being converted on the first try, since only 15% of the hydrogen gas and the nitrogen gas is actually being converted into ammonia, and that requires that whole recycling system to be in place to make sure that not all of the reactants is lost and is able to be, and the process is not wasteful. But chemists and other chemical engineers and different types of scientists should still keep on working on how they can make the process a lot more efficient overall, so that it can be more profitable and more helpful in producing more of the ammonia. Thank you for listening to our presentation, and here are all the references that we have used throughout our PowerPoint presentation. Thank you again for listening to our presentation.